Muthulashmi, Assistant Professor of Mathematics SF, V.V. Vanniyapperumal College for Women, Virudhunagar. In this video, we are going to learn about linear recurrence relations. First, let us see definition. A linear homogeneous recurrence relation of degree k with constant coefficients is a recurrence relation of the form an equal to c1 an minus 1 plus c2 an minus 2 plus etc. plus ck an minus k. Here c1, c2, etc. ck are real numbers and ck not equal to 0. Okay, now let us see the examples. The recurrence relation Pn equal to 2 into Pn minus 1 is a homogeneous recurrence relation of degree 1. Now another example, the recurrence relation An equal to An minus 1 plus An minus 2 the whole squared, which is not linear because An minus 2 occur twice the time. Okay. Now another example, the recurrence relation Hn equal to 2 into Hn minus 1 plus 1, which is not homogeneous because here the constant term 1 is occur. Okay. In last example, the recurrence relation Pn equal to n into Pn minus 1, which is not homogeneous because this recurrence relation does not have constant coefficients. Now, one important note we can say, An equal to r power n is a solution of recurrence relation if and only if Rn equal to, r power n equal to C1 r power n minus 1 plus C2 r power n minus 2 plus etc. plus Ck r n minus k. Okay, now after getting simplifying, we obtain r power k minus c1 into r power k minus 1 minus c2 into r power k minus 2 minus etc. minus ck minus 1 into r minus ck that equal to 0. Okay, which is also called characteristic equation of the recurrence relations. Okay. Now we are going to see one theorem statement. C1 and C2 be two real numbers. Suppose that r squared minus C1 r minus C2 equal to 0 has two distinct roots r1 and r2. Then the sequence An is a solution of recurrence relation. So An equal to C1 into An minus 1 plus C2 into An minus 2. If and only if An equal to alpha 1 into r1 power n plus alpha 2 into r2 power n for n equal to 0, 1, 2, etc. Here alpha 1 and alpha 2 are constants. Okay. Here our recurrence relation is An equal to C1 An minus 1 plus C2 An minus 2. At the time sequence An is a solution. Here the characteristic equation is r squared minus c1 r minus c2 equal to 0. Here c1 is the coefficient of an minus 1. Here c2 is the coefficient of an minus 2. Okay. Using this theorem, we are going to solve one problem. Here our problem is, what is the solution of the recurrence relation? An equal to an minus 1 plus 2 an minus 2. Here initial condition is a not equal to 2, a1 equal to 7. Okay. Now we can see the solution. First we are going to write the characteristic equation using this theorem. Here the relation is an equal to c1 an minus 1 plus c2 into an minus 2. For this recurrence relation, characteristic equation is r squared minus c1 r minus c2 equal to 0. So here our recurrence relation is an equal to an minus 1 plus 2 into an minus 2. Here c1 value is 1, c2 is 2. So the characteristic equation is r squared minus r minus 2 equal to 0. Okay. This is a quadratic equation. Now can solve this equation. Find the two roots because here degree is 2. Okay. Here our characteristic equation is r squared minus r minus 2 equal to 0. This is a characteristic equation. This is also quadratic equation. Here using sum and product rule, find the roots. Okay. Here the product is minus 2. Sum is minus 1. We can take two numbers, 2 and 1, minus 2 and 1. Okay. Minus 2 into 1, minus 2. Minus 2 plus 1, answer minus 1. Okay. So, this can be written as r minus 2, r plus 1 equal to 0. From this, r equal to 2, r equal to minus 1. Okay. Here, our roots are distinct. Here, the roots are 2 and minus 1. So R1 equal to 2 and R2 equal to minus 1. Hence, the sequence AN is a solution of recurrence relation if and only if AN can be written as alpha 1 into R1 power n plus alpha 2 into R2 power n. Here R1 is 2, R2 is minus 1. So AN equal to alpha 1 into 2 power n plus alpha 2 into minus 1 power n. Okay. Here in our problem, initial conditions are A0 equal to 2, A1 equal to 7. Using these initial conditions, find the alpha 1 and alpha 2 value. Okay. For solution, AN equal to alpha 1 into 2 power n plus alpha 2 into minus 1 power n. Our initial conditions, A0 equal to 2, A1 equal to 7. Okay. Now, put n equal to 0 in this equation. So, A0 equal to alpha 1 into 2 power 0 plus alpha 2 into minus 1 power 0. That equal to anything power 0? Answer 1. Already we know. So, alpha 1 plus alpha 2. Here A0 value is 2. So, our equation is alpha 1 plus alpha 2 equal to 2. Okay. Now, let us mark equation number 1. Okay. Now, again put n equal to 1 in this equation. So, A1 equal to alpha 1 into 2 power 1 plus alpha 2 into minus 1 power 1. That equal to 2 alpha 1 minus alpha 2. Here A1 value is 7. So, our equation is 2 alpha 1 minus alpha 2 equal to 7. Now, let us mark equation number 2. Now, adding equation 1 and 2. So, 3 alpha 1 equal to alpha 2 cancel. So, 2 plus 7, 9. Okay. So, alpha 1 equal to 3. Now, put alpha 1 equal to 3 in equation number 1. So, 3 plus alpha 2 equal to 2. So, alpha 2 equal to 2 minus 3. So, answer minus 1. So, alpha 1 is 3, alpha 2 is minus 1. Again, substitute in this equation alpha 1 and alpha 2 value. So, AN equal to 3 into 2 power n plus minus 1 into minus 1 power n. This is a solution of our recurrence relation AN equal to AN minus 1 plus twice the time of AN minus 2. Thank you.